What is the probability of a type 1 error? What is the probability of a type 1 error? That's alpha, absolutely. And what does that mean you did? That means you rejected the null hypothesis incorrectly. You made an error, and you made a type 1 error. That's the rejection. That is the probability of making a type 1 error is alpha, and that is that you reject the null hypothesis incorrectly. What is the probability of a type 2 error?
Yeah.
Remember, alpha is the first letter of the Greek alphabet. But beta is the second letter of the Greek alphabet. This is when we fail to reject the null hypothesis incorrectly. Again, this is an error, so we did something wrong. We did not reject the null hypothesis, but we should have. We failed to reject the null hypothesis, but we should have. So these are our probabilities of making errors. Now I'm going to give you the probability of doing something right. So the probability of rejecting the null hypothesis correctly is called power. Power. The probability of rejecting the null hypothesis correctly is called power. Do you guys want to be correct when you make a decision? Most of the time, yes. Usually when you guys make a decision, you want to be right. So do you think you want your power to be high or low? You want high power. You want power to be really high. Now, power is very special to beta. They are complementary of each other, meaning if I take power and I add beta, I will get 1. I'll show you why here in just a second on our table. If I take power and I add beta, I get 1. So let me ask you guys this question. Mathematically speaking, what does power equal? Mathematically speaking, it's 1 minus beta. Mathematically speaking, what does beta equal? 1 minus power. Very good. Cool?
Say it again, please.
Power plus beta equals 1.
Okay.
So that means power is 1 minus beta.
Okay.
And beta is 1 minus power. Think about just subtracting to the other side.
Okay.
Okay. All right, cool. So let's look at this table. Remember this table from last time? I don't remember when we did it, but our null hypothesis is true or our alternative is true. That is not saying that I'm accepting the null hypothesis, but let's just be real. In actuality, you either are going to have a correct null hypothesis or a correct alternative, but we don't ever make that decision because we're basing our decisions on our sample, and so we are making a decision to either reject the null hypothesis or fail to reject the null hypothesis. So we did this either earlier this week or last week, I don't remember. But if we reject a null hypothesis that is actually true, what have we done? That's our type 1 error.
Is this not the same thing?
This is exactly the same thing. We're going to add one thing to it, though. The probability of this type 1 error is alpha. The probability of this type 1 error is alpha. If I reject the null hypothesis in favor of a true alternative, what have we done? We have done a good job, and this is exactly power. This is where power is. If I correctly reject the null hypothesis, that's power right there. All right, If I do not reject the null hypothesis, I fail to reject it, and it was true, and I didn't reject it, what happened? I did good. I did good. Now, there's no probability of, there's no word here, okay? So don't worry about that. And then the last square here, I failed to reject the null hypothesis when the alternative was true. That's our type 2 error. And we just said the probability of a type 2 is equal to beta. So here is why power and beta add up to 1, right here. When you have an alternative hypothesis that is the true thing, you're going to do one of two things. You're either going to reject the null hypothesis in favor of that true alternative, or you're going to mess up and not reject your null hypothesis in favor of that true alternative. You only have one of two options there. That's it. When somebody is on trial and they are guilty, only one of two things is going to happen. They're either going to get proven guilty, or they're going to be proven not guilty incorrectly. That's the only two options.
Proven not guilty incorrectly.
Correct. So
they are guilty.
Correct.
Okay.
Yes. So that is why these add up to 1. So again, power plus beta equals 1. I can only make one of those two decisions when my alternative is true. I'm either going to reject the null and take that alternative, that's true, or I'm going to fail to reject the null and not take the alternative, and that would be a bad decision. Okay, so power, important. Power is important, and sometimes I want to make sure that I am getting it right. Sometimes the right decision is the most important one to make, and so I'm going to want to increase my power. This is the probability of putting a guilty person in jail. So let's say the death penalty is on the line. Don't you think I want to get it right? I probably want to get it right. That's why when death penalty cases are on the line, you have to really, really, really prove your case. It has to be beyond any shadow of any doubt that you believe that this person is guilty. So sometimes we want to increase power. So to increase power, we can do a couple of different things. The first thing we can do is we can increase our sample size. When we increase our sample size, we decrease the chance that we're going to mess up because we have really good representation from the population. So when we increase our sample size, we decrease the chance of messing up and powers the probability that we don't mess up. We can also increase the significance level. Now, hang on a second. What is the significance level? That's just alpha. So how does that work? Alpha is the probability of a type 1 error. If my type 1 error probability goes up, type 2 error goes down. And the probability of a type 2 error is equal to beta. So if alpha goes up, beta goes down. Now, if beta goes down, what's going to happen to power, which is the complement of beta? It's going to go up. So if beta goes up, beta goes down, my bad. If beta goes down, power goes up. Now this is like one of those SAT analogy things right here. If alpha goes up, beta goes down. If beta goes down, power goes up. So what happens to power when alpha goes up? It goes up as well. So that is why when I increase my significance level, I'm increasing my power as well. So here's kind of to summarize all of this. Alpha, the sample size, and power move in same direction. Beta moves opposite. Have any of you ever had a betta fish? Can you put them with other fish? No. Nope, they have to stay by themselves. So betta is by itself. It moves by itself in an opposite direction of this little fish, which is not really a fish. It's not a fish. Okay. Okay, cool. Let's do an example, guys. ADHD. Anybody heard of ADHD? The Centers for Disease Control and Prevention claims that 11% of American children aged 4 to 17 have attention deficit hyperactivity disorder. A company claims that it has developed a new vitamin tablet that will lower a child's risk of developing ADHD. Researchers will administer the vitamin tablet to 200 volunteer children under the age of 4 with parental consent. The subjects will be tracked through childhood, and the researchers will record the proportion of the subjects who develop ADHD. The researchers will perform a test at alpha equals 0.05 significance level. The null hypothesis is that the true proportion is 11%. Shh. The null hypothesis is that the true proportion is going to stay 11%, but their hope is that the vitamin is going to decrease the proportion under 11%. Oh, really? Then why don't you come on up?
Do it.
I'm okay.
Do it.
Uh-huh.
Do it.
I'll let you.
Thanks. Appreciate it.
Come
P
in.
is the true proportion of all children like those in the study who would develop ADHD when given the new vitamin tablet. The new vitamin tablet is expensive to produce, so we want to make sure we are really convinced that it's going to reduce the risk of ADHD. The power of the test to detect that, this should say P, you guys. It should not be another alpha. That should be a P. That P equals 0.05 is 0.937. Now, let me explain to you guys what that last little statement says. Basically, what we have is we have a distribution that is on 11%. We have a null hypothesis that's at 11%. This is the proportion of kids that get ADHD. What we're saying by this power statement right here is that if the actual proportion after taking the vitamin goes all the way down to 5%, then we have a 93.7% chance of proving that. That's what that means. Come on in. Hi. How are you? Hello, hello.
Hello.
Come on in.
And walk in, guys. Walk in.
You're so funny. All right, so let me say that again. The null hypothesis is that the true proportion is 11%. That's what has always happened with the ADHD. We've had 11% of the kids are having ADHD. We're giving them this new vitamin to prove that the true proportion has decreased. Ma'am?
I'm listening.
To prove that P is all the way down to 0.05, we would have a 93.7% chance of proving that.
It's not like I'm the only one talking. Everyone's talking.
I love you. All right, so the chance of proving that P decreased from 0.11 to 0.05 is 0.937. That's our chance of proving that this vitamin decreased our ADHD from 11% all the way down to 5%. Is that a pretty good chance? That's a pretty good chance. I mean, 93.7% chance?
That's a great chance.
That's a pretty good chance.
That's a great chance.
If that's the case, then would I want to go ahead and produce this really expensive vitamin? What do you think? If that's the chance that I've proven this to be true, would I want to do this expensive vitamin? Yeah? Yeah? Okay.
Say so.
Okay.
Let's do it.
Cool, let's do it. I'm with you. All right, what is the probability of a type 1 and type 2 error? Y'all can find this. Ready, go. You can do this. It's easy. Probability type 1, type 2 error.
I know.
You don't need a calculator for this, man.
Okay.
All right, what's our probability of a type 1 error? How'd you get that? That's just alpha, right? So the probability of a type 1 error is just alpha, which is 0.05. Easy. Okay, cool. Type 2 error. What's the probability of type 2 error? How in the world, Grace, did you get 0.063? I didn't see 0.063 anywhere in the problem. Nice. So Grace remembered that just a minute ago we found out that beta, which is the probability of type 2 error, is 1 minus power. And so we take 1, we subtract the power, 0.937, and we get 0.063. Nice. Good job. Okay, what happens if we use alpha of 0.1 instead of alpha of 0.05? What's going to happen to power? Increase or decrease? Increase, increase. I hear that twice. Going 3 times?
Increase.
Increase. Are we sold?
Sold.
Sold. All right. If alpha goes up, power goes up. Remember those move in the same direction? So power would increase. Is this a good thing?
Yes.
Why? Why is this a good thing? Thank you. Of course. Y'all have a good day. Why is this a good thing?
It just is. You embarrassed me like you're in front of guests.
Everyone was at me and Andrew calls me out.
You were the only one talking.
No, I wasn't.
Bet.
People, they're talking.
They were before.
Not when
It's fine though.
When they
I love
came in,
you.
I was silent.
I love you.
Silent.
I love you.
I already know.
You know why? Because first impressions matter. I never met those people.
I'm glad.
And now they think I'm a great student.
Oh my God, I'm gonna throw up.
And now they think I'm a
Anyways,
bad
why
student.
is it good if we increase power?
It means that you're correctly rejecting.
I am correctly rejecting the null hypothesis. You're right. You're right. All right, cool.
I'm just.
It's fine. You're amazing. All right. This one's a little bit tricky right here. If the true proportion of P, if the vitamin changes P to 0.08 instead of 0.05, what happens to power then? So, think about it this way. We've got our true proportion is currently at 11%. If I get the true proportion to decrease all the way down to 5%, and I can prove this, it's going to be pretty easy to see a big difference here, right? So like if I take a sample, I should be able to pretty easily tell if it's over at 11 or over here at 5, because there's a pretty big difference there. But if I'm here at 8%, then it's going to be a little bit harder to tell if there's really a difference because of the vitamin or if it was just sampling variability. So it's going to be a little bit harder to prove that I have actual change. So what does that mean about power? Will it be easier to prove the alternative or harder to prove?
Harder.
Very good. All right, so power would decrease because 0.08 is closer to the claimed value. .08 is closer to the claim value, so it's harder to prove that there's a difference. It's kind of like if a crime happens in the downtown McKinney area, and you are over at McKinney High School when it happens. You're closer to the crime and might be part of the suspect pool. But if you're all the way over in Frisco, it's pretty hard to prove that you were a part of that crime. Okay?
Depends how long ago the crime happened.
This is a good point.
And that's
Whoops.
with any case.
My
A
bad.
good detective would
Yeah,
figure
well.
it out.
What if we use n of 500 instead of n equals 200? What would happen to the power of the test? Yep. So when n increases, power increases because we have better data to prove the alternative hypothesis. We have better data, more data, better data to prove the alternative hypothesis.
Wow, that was